All right, welcome back, everybody. We've got a number of fun and interesting review and practice problems to move through today, so I want to jump right into it. Welcome back to being in lecture together. As we move forward, the sort of cadence that you can expect is lecture or practice lessons that are async on Tuesdays. We'll be in class on Thursdays. And the cadence of exercises is they should be released on Tuesdays, and they'll go along with the async lessons, so they give you a chance to practice and apply what you've just learned in those videos. And then we do the following Monday, and holding as best we can to that. Along those lines, we do have exercise 2 out. It's what we call one-shot Wordle, because you get one guess at the word, but you can always play again. So it's sort of like a poor man's Wordle. We'll get to being able to make multiple guesses and closer to the real Wordle in the next assignment. That grader was supposed to be put out by Friday. I was able to knock it out last night. Some of you have asked, why do we hold on to the grader and wait to release it? And the reality is it just doesn't exist when the write-up exists. So these are all new exercises to start the semester. Wordle was something that came onto our radars a week or two before classes started, and we thought, oh, this would be a fun way to apply the same concepts we're learning fundamentally in 110 to exercises. And so as soon as I have the write-up ready, it's posted, and as soon as the auto grader is ready, that takes some programming in the background, it gets posted as well. And we'll try and get those out as quickly as we can so that everyone has a chance to go for the extra credit. So today's goals are a couple of quick announcements. We'll be practicing and reviewing the control flow statements you've learned. That's if-then statements and while statements. Also, I'm going to apologize. I came in on my scooter and my face got really cold, so I'm kind of sniffly. Hopefully that doesn't come through on the mic, but we're in a COVID time, so I just want to say that not COVID positive, and we're just fine. We will be learning about 2 new concepts today that are just sort of minor tweaks. They're what we call syntactical sugar. Not because they give us anything new that we couldn't do before, but because they make our code a little bit sweeter. So we'll be looking at that. 2 ideas there. I want to remind you of a couple of important resources that exist for you. Tutoring. Many of you have come to work with us in tutoring. This is a place for conceptual questions that is at a relaxed pace. There aren't time restrictions on how much time you can spend in tutoring. If you want to come and work with us for an extended time, that's great. This happens on Mondays and Wednesdays from 4 to 7 p.m. in Fred Brooks 007. So hopefully you all figured out that Fred Brooks and Sitterson Hall are the same building. It's just 2 different sides of the same building. And so if you come into one, you're going into the other. And everything that we do resource-wise happens on the very first floor or floor 0. Floor 0. Again, what tutoring is like is it can be one-on-one interactions depending on how busy it is. It might be small groups working through some practice problems, going over concepts is a great way to go over your quiz. And we can help you with practice problems like quiz practice preparation problems. If there are questions in lecture that didn't make sense and you want to talk through those again, it's also a great resource for that. The one restriction on tutoring is that we can't help you with exercises here. We do all the exercise help in office hours. So the full schedule is on Course.Care. We're open for over 40 hours a week. When you run into roadblocks on exercises or just have conceptual questions, come for one-on-one help. We tend to limit interactions to 15 minutes, and the reason for this is to try and help you get past whatever your current roadblock is, but be sure that you're able to go out and work on the rest of it on your own after that, right? And we're primarily concerned with being sure that you understand the concept that's blocking you from making progress, more so than being sure that you get on to the next thing. And sometimes if it becomes apparent that something much earlier in your program, or there's some fundamental concepts that look like you could use a little bit of extra conversation about and tutoring on, we'll focus on that rather than the actual problem at hand, because they're all related. You can go to office hours for conceptual questions. If there's not a queue of people waiting, we can go a little bit longer on these. They're not as limited to 15 minutes. But if there is a queue of people waiting behind you, we will limit meetings to 15 minutes to try and be sure that we're fairly allocating our time to everyone. In the past week, 170 of you have made use of office hours. That's awesome. That's nearly a third of the class. And the wait time has been 1 minute with a standard deviation of 1.5 minutes. So we've been well staffed, and it's been really excellent to work with you all one-on-one. Again, because I didn't get to talk through your section on this in the very first class, the way office hours works, many of you have figured this out, but if not, you come to Citizen Hall, you open up Course.Care when we're open, and you submit a ticket. The ticket should be well articulated. It should make a real effort to describe what's going on based on the questions that you're asked, and that helps us understand what the problem is you're working on. It helps you be prepared to make the most out of this time so that you can get right into talking about the problem and articulate it, and we'll call you in as quickly as we can. Right? Any questions on tutoring or office hours? All right. There's one other thing that I wanted to address. Someone passed along a yak to me that was asking if anyone else was obsessed with Lordo because of COMP110. I'm pleased. I loved seeing this post. Shared it on my Instagram, and I hope that you all are counting down the minutes and hours until the 12:01 or 12 o'clock ability to refresh and replay Wordle. Another yak came across my radar, and I want to just say for the record, for the person who posted this, you don't have to worry. I'm an Android user. Yik Yak does not exist on Android. But, I think this said I will smile to myself, but if it said something else and you need to excuse yourself, that's okay. And one other one was shared with me, which I will say, be sure that if you're listening at 2x speed, you're not getting half the comprehension, and or watch it twice. I do know that moving through content at 1.5, 2.5, or 2 speed is a good way to get through content more quickly. Just be careful not to cut your understanding short. All right, so let's jump right into a practice problem, and we're going to do this with pen and paper or pencil and paper. So I'm going to encourage you to set up an environment diagram, and let me just make sure I get the camera out of the way. And what I want you to imagine when tracing through this is that on line 3, when the users ask for input, they enter the number 3, all right? And trace it as if they entered the number 3 into the input prompt. And keep track of the variables as well as what the printed output is. And we'll spend a few minutes working on this. Once you think you've got it, or if you get stuck, talk to your neighbor about it. If you have questions, ask us about it. I do want to point out, actually, one important thing, which is notice that this while loop, its repeat block is all of these statements. And the nested while loop has 2 statements inside of it, right? So be careful of that and trace through this as you expect it to work. And we'll come back and talk about it in a few minutes. Additionally, we have a great cast of UTAs here today, so if you have questions, do raise your hand and we can come talk you through something going on. 2 more minutes on this, and we'll talk through it together. Once you think you've got it, I would encourage introducing yourself to your neighbor if you don't know them, and talking through what your output was. One more minute on this, 1 more minute. For those of you who are on the stream, you can ask questions in the discussions tab on Course.Care. All right, let's talk through this. So there's something that is interesting and fascinating going on in this example that includes a technique that you're going to make use of in the current exercise if you haven't started it yet, which is this idea of a nested while loop. But before we get there, and this is something I'll encourage when you see code tracing problems, before you jump ahead and try and figure out something in the middle, work your way to it first and be sure that you know the steps to get there. So on our diagrams, we're going to have a globals frame. So far, this is all we have. Starting next week, we'll see that there are some other frames on our stack, and I could label this the stack as well. And in the week after, we'll actually, next week, we'll see some reasonings for why we have this area called the stack and another area called the heap. But for now, we're really only concerned with the stack and this globals frame. We have this I variable that's established, and it's the user's input. We're taking their input as a string, which we said the user typed in the number 3, and then we converted it to an integer with the int constructor, so I is 3. We then have this variable s that's, I'm going to give myself some extra space here, just for, I know where this program's ultimately going, but we're going to be replacing s a number of times. This is just a string that's initially the empty string. Now, something that is very important that some of you may have noticed is something we look for in diagrams on quizzes is when we're working with strings in memory, specifically, like when you see string values in your diagrams, we would expect quotes to be around them. When it comes to output and printed output, we're a little bit less concerned about the quotes. Technically, if you print a string, and you all have done this, right? Starting with the very first hello world exercise, when you printed the string hello world, which had the quotes around it, those quotes don't show up in output, right? The quotes are important for us in memory to signal that, hey, yeah, this is definitely a string type of value. By the time you print output, everything winds up being textual in nature, so we're a little bit less discerning there. But in memory itself, on the stack, you don't put quotes around an int. You only put quotes around a string, but be sure you're doing that. Don't put a decimal point around or by an integer. That might confuse us, and we think that you're expressing a floating point value, and so on. All right, so we get to this while loop on line 6, and we're asking, is I greater than 0? So this expression, right, gets substituted, and I, we look up the current value of I, that's 3, 3 greater than 0, that's true, so we jump in. And we go ahead and we see a line that we're going to evaluate a number of times, which is this concatenation. We're taking the current value of S, which is the empty string, and concatenating H to it. So now S is going to be, I'm just going to write it in here, and I'm actually going to start crossing this out and keeping track of all the different values in just a moment. Actually, why don't I go ahead and do that just for completeness sake. So it's no longer the empty string, now it's H. In terms of how you do this on your diagrams, if you've got a good eraser and you want to just erase and replace in place, that's totally fine. If you'd rather just cross out and write the next value, and you'll see that pretty quickly we're gonna go off the edge here, and that'll be fine. All right. We then see this variable h being established and initialized to 0, so I'm going to go ahead and set up h as 0. And we reach another while loop. All right, so this while loop is a nested while loop. Notice it's contained fully within the repeat block of the outer while loop. And we're asking, is h less than I? Well, we just initialized h to 0, so 0 less than 3 is true. And we go in to this loop, and we say, okay, we take s's current value, that's h, and concatenate e. So s is no longer h, it's now, I'm going to write this beside of this, it's now he, right? And we then take h's current value, which is 0, and add 1 to it, and replace h's value with that. So h is now 1. All right, we've incremented h by 1. Now here's where the real crux of this little example, and the important thing to understand, happens right here. Where do we go next, right? And hopefully you correctly identified that when you reach the end of a while loop's repeat block, you go back to the corresponding test condition, right? We haven't completed this loop yet. We don't jump back to the very topmost and outermost loop. We go right back to the loop that we're working on. And so we haven't finished this loop, right? We still need to ask and reach the terminating condition of this, which is once this condition, h less than I, is no longer true, then we'll be done with this inner loop and we can continue on. But for now, we have h that value is 1 now, less than 3. That's true, so we go into this loop. And we once again concatenate an e, so now our string is HEE, and then we increment h by 1, right? So h is now 2. All right, I'm gonna do this one more time. We go back up, we test again, is h less than I? H's value is 2. Notice it's getting closer and closer to 3, so we're making progress towards our goal. We have reason to believe this isn't an infinite loop. So we compare 2 less than 3, that's true. We go back in and we replace the string HEE with HEEE, and we add 1 to h. So h's value is now 3. All right? We go back up. We test one more time. Is 3 less than 3? And finally, we've reached the end of this, right? We're done with this inner loop because this is no longer true. 3 less than 3 is false, so we would continue on to line 12. Now I'm going to pause right here. We're at line 12, and we're about to evaluate this line and continue on in this example. But before I do so, any questions on what we've seen here so far? Yep.
Since h is declared within the while loop, would it still be under the blown loop stack?
So for our purposes, yes, and in Python, yes. In some other languages where, and we'll talk a little bit more about an idea of scoping, you could imagine that there's sort of ways in which h wouldn't exist in quite the same way as these other variables, but for our purposes and in Python, yes. All right, question back here.
When we are finding the variable s, you add s to h, to string of h.
Yep.
Why doesn't that go in, why doesn't that change the variable of labels to s, h? Why is it just?
Good question. So the question is, on line 10, where we're concatenating, actually above that, the very first line, where we're concatenating, so line 7, if we go back to line 7, but the same logic applies here, something that's very important to recognize, and I think this is a great example of it. So let me just write this out in very large. S is assigned S concatenated with H. So part of the reason why these quotes are so important is that when you see them, we know here that we're talking about the string character data H. So it's the letter H as a string value. Whereas notice there's no quotes around this S. And that means we need to go look up in memory, what is S? Well, S is the string variable that we've set up. We established it on line 4. And we're referring to that specific string variable and saying, hey, whatever that string variable currently has in its placeholder, which initially it was nothing, right? There's no text in that string. Take that and concatenate H to it. So that's what gave us just the string H. And then down here, and we'll see that actually this is going to be different. We're about to go back up and do this again, and S no longer is going to be empty, right? It's going to have H-E-E-E in it, and we're going to be adding an H to the end of that. So the key thing to be looking for and be careful of is when you're reading the code, if you see the quotes, know you're working with some text data. If you don't see quotes around a word or a letter, know that you need to go look up that variable's value in memory and figure out what it refers to. Good question. All right. So let's continue on. And here we're saying take i's current value and subtract 1 from it. So i's current value is 3. It drops down to 2. And we go back up. We reach the end of that while loop, and we go back up to the top of that while loop, and we have to ask ourselves, is I greater than 0? Well, I is 2, so that's true. It is greater than 0. We go back in, and here we reach this line again. S is assigned to the current value of S concatenated with H. Right? Well, the current value of S is he with 3 E's, so we're replacing that value to be H-E-E-E-H. Right? We're taking that current value of S, adding an H onto the end of it, and then replacing S's value with it. We're once again reestablishing H to be 0, so I'm just going to replace H. It's now back to 0, and we reach this while loop, right? Well, H is less than I, so H is 0, I is 2. We're going to go back in. That's true. We go back in. We concatenate E. The string is starting to get long, so we now have H-E-E-E, H-E. We add 1 to H, just like we did before. We go back up to the top, and we test again. Is H, which the current value of H is 1, less than 2? That's true. So we go back into our loop, and we test one more, and we concatenate another E. So we have H-E-E-E, H-E-E. And then we add 1 to H again, so H's value is now 2. We go back up to the top of this loop. Is 2 less than 2? That's false, right? So we're done with this inner loop. We had to do a little bit less work this time. And we go on and we subtract 1 from I. So I's value is now 1. All right? We've reached the end of that repeat block, so we go back up to the top and test, is 1 greater than 0? We're getting very close to being done with this outer loop, but we're not there yet. So let's jump in. And once again, we're at line 7 and concatenating an H onto the end of this string. So now it's H, 3 E's, H, 2 E's, H. And H is reinitialized back to 0. So I'm gonna bring this around because we're starting to have a lot of values of H here. And we test, is H less than I? H is 0, I is 1. So that's true. We go into the block, the repeat block. Once again, we concatenate E. So we have H-E-E-E, H-E-E, H-E. We add 1 to H. H's value is now updated to 1. Oops. And we go back and we test, is 1 less than 1? That's false. So good news, this is starting to get very long. We're almost done. And we finish that inner repeat block. So we go down to line 12, subtract 1 from I. I's value is now 0. We go back up to the top of this loop. We test, is I, which is currently 0, greater than 0? That's false now. So we're done, and we print S. So S's value at the end of all of this is he, right? That's the output of this program. The point of this example was to emphasize the ways in which inner loops or nested loops work, to also give you another example of a loop that counted down rather than counting up, and that was okay. And you get the sense that if we had input 100 here, wow, it would have been tedious to actually work through that. We would never ask you to do that by hand, but the computer is more than happy to and would do so instantaneously, effectively. Questions on this example before we continue on? Yep, question here.
Yeah, this is similar to an earlier question, but outside the while loop, would age be accessible?
So in general, you should not expect it to be. If you wanted it to be, you would really want to declare it outside. I believe in Python it actually would be accessible, though. Those rules wind up being very specific to the language you're working in and a little bit beyond our concerns. But to get, so for those of you who are online and didn't hear that, and just for the recording purposes, the question is, could you access H? Like, could we print H down here? And what I'm going to tell you is, if you wanted to do that, you'd be best off declaring H up here and just reinitializing it to 0 in the loop. And that would be best practice. I don't actually remember with full certainty whether or not this would work in Python. I actually do think it would, because I think all variables within a given scope wind up being not block leveled inside of loops. It's a little bit beyond our concern, but if you did need to use it outside of the loop, you should declare it outside of the loop before it begins. All right, other questions? All right. So what we saw happening in many places in this example was we were reassigning a variable relative to its current value. This is super common. Like, you want to take a value x, add 1 to it, and reassign that back to x. You want to take a string, you want to concatenate something onto the end of the string. You're having to do this in the current Wordle, where you're concatenating emoji onto to build up a string. This is super, super common. The example we just saw, if you're looping with a counter variable, let's say you wanted to count up by 2s rather than 1s, or subtracting 1, which we saw in this past example. Also, when your variables start getting much longer, so you can imagine just summing up or adding on to some sum you're accumulating, and what we just saw, concatenating with a string. This type of operation is so common when you're programming that Python has a nice shorthand for achieving this without as much repetition. And these first examples you see, you might think, wow, it's not like there's a lot of, it's not that tedious to write out I 2 times in this given line of code. But when you start having longer variable names and more complex expressions on both the left-hand side and the variable that you're modifying, it can be pretty tedious. And so there's a nice shorthand syntax for this called relative reassignment operators that you'll see me and the TAs using in the future, and I would encourage you to try and embrace. The idea is, rather than writing I is assigned I plus 1, we can achieve the exact same outcome with I plus equal 1, right? Means the same thing, no difference. You're not gaining any capability, you're just saving yourself a little bit of code and potentially some typos, right? Where this really pays off, as I mentioned, is when you have longer variable names, such as total dollars. If you're trying to take the current value of total dollars, add the next donation up to it, and reassign it back to itself, that starts to become more tedious to type out. And so relative reassignment works well in this case. This operator works with most of the operators you would expect it to. So imagine a variable named I that is, say, an integer. You could use it with all of the regular integer arithmetic operators, as you would expect. It also works with strings and concatenation as well, right? So just as an example of a before and after, the code listing we just looked at could have been rewritten with a little bit more conciseness. Again, this really doesn't pay off with single-letter variable names. In memory diagrams, we tend to choose single-letter variable names just because it's less writing in your diagram to keep track of. But you can see that there's no difference in these programs. It's just a little bit shorter, prevents potential errors and typos, and is worth knowing because you'll see it all over the place. And the same concept exists in other programming languages as well. Any questions on relative reassignment? All right. All right. So I have two code listings here. And in this next little exercise, I'd like you to try and imagine if there's a response that would produce different outputs in these two programs. So imagine the same response value, and the question is there any response value that would give you output that's different, even if the response variable was the same? And I want you to discuss amongst yourselves, why is it that there might be, and what is the difference between these code listings? So let's spend a minute on this and try and discuss with your neighbor. All right. Just ran out of battery here. There's a chance I wind up going to the hand mic in just a moment. Raise your hand if there was an input you could imagine that did lead to different outputs in this example. All right, I think I'm seeing most hands here, and you would be correct. Does anyone want to take a stab at trying to discuss or explain why there's a difference here? Sure.
So on the left-hand side, 0, it would print most definitely, but then it would also go down to the 2, and since 0 is not equal to 2, it would also print no. But on the right-hand side, because the if-else's are embedded, if you printed 0, it wouldn't print no.
Great. Yes. So, and what's your name?
Catherine.
Catherine posited that, let's imagine we had input 0 for response. Well, if we had done so, in the left-hand example, we would see that this line is printed, right? Because 0 is equal to 0. Well, we continue down, and the computer's going to check. Well, is response equal to 1? No. Okay. Is response equal to 2? No. Oh, well, there's an else statement on this if, so it would also print nope, right? So if we entered 0 here, we would get most definitely and nope, right? Now, if we compare that to this example, if we entered 0 here, we would print most definitely, but notice this else block contains all of the other logic, so we would skip right past it and continue on in the program, and nope would not print. In fact, as this is written, the only way it would get nope is if we provided some number that wasn't 0, 1, or 2. Whereas in this example, on the left, if we had given a response of 1, we would have printed quite possibly and then nope, right? Any questions on this? So the key difference here in these two examples is the relationship of this nesting of these if statements inside of the else branches rather than sequential if statements. And this is something that we saw commonly on the first exercise where in some cases we saw a sequence of if statements which for checking the indices, before we had loops, you needed to do that. But at the very end, when it was trying to print whether or not the output was the correct pluralization, we saw a lot of independent if statements. More ideally, if your program is going to go in one of many different directions, you would want to nest that logic so that as soon as the computer says, okay, this is true, we're going to print most definitely, and then we're going to move on. We're not even going to look at these other conditions, right? But in this case, the computer would still be checking, even if response was 0, and we printed most definitely, it would still check if response was 1. It would then go check if response is 2. And you can imagine if this was if response is 3, print nope, or if it's 4, print nope, or whatever. And unrelated if statements that are following one another, the computer's going to evaluate each one by one, no matter what. Whereas in a nested if then else, as soon as you reach a then that is true, so like let's imagine it was 1, this would be false, so we would skip over that. We would go into this if block. If response is 1, we would print quite possibly, and then we would skip out of that and not evaluate what followed. So it winds up being a little bit more efficient as well. And what I've kind of just explained and is in the slides, and one of the other things I'll mention, because someone asked in chat about whether the slides were accessible, you can find the slides linked to on today's, just underneath the stream link on today's entry on the course website. But when you have a branching point in your program and you really just want one of a few different options, you really want to nest your logic with related if-else statements rather than have a bunch of unrelated if statements. Not only is it a little bit more efficient, but it will also avoid accidental logical errors. For the example, the one that we just saw, you probably didn't want nope to print if response was 0 or 1, but it would have, like we just worked out. All right, so next I want to try implementing with you an example of this so that we can discuss one other code construct today. But first, I want to give you an example of where we're going. So hopefully some of you have seen an 8-ball, a magic 8-ball that tells you the answer to a yes-no question. I'd love for someone from the audience to provide a yes-no question for me to ask the 8-ball. Got a question back here, yep. Will, what's your name? Alex, get a 4.0 this semester. This is a dangerous question to ask an 8-ball. All right, we ask. Oh no. Let's ask again. Uh-oh. There must be some logic in here. Oh no. Wow. That 8-ball is more depressing than the one we're going to write together. So what I'm going to encourage you to do is join me in VS Code. And in your lessons directory, I'm going to ask you to make a new file. So right-click, new file, and let's name this 8ball.py. Right? So again, lessons directory, 8ball.py is the name of this program. And I want to point out, let me get my pen here. Oops. That whenever we're in an example like this, and whenever you're actually working on code, part of VS Code, which tries to be very helpful, is just below your tab, the line below your tabs, this is telling you the path to the file that you've got. So we know that we're in the lessons directory, and this is 8ball.py. All right, so we can add a quick doc string here and say that this is an oracle that predicts the future. And we first have to get a question, right? We need a yes/no question. So we can ask the user for some input. Ask a yes/no question. All right, you might be thinking, why aren't we storing that input in a string or somewhere where we could use it later? It turns out 8-balls aren't listening. They're just random objects, right? They don't care what you ask. And so we don't either. We're going to ask the question, and then we're going to generate a response. In order to generate a response, we need the ability to, when you shake up an 8-ball, there's some randomization that's going on, some natural entropy that causes the die that's in the middle to spin to a certain direction and float up to the top of the 8-ball and present you an answer. Well, something that we'll be talking about in much more depth soon is how we can import functionality from one place or from libraries in Python. For now, I'll give you sort of a hand-wavy explanation that above the input, we tend to put these lines at the tops of our programs beneath the doc string. We're going to say from random, import randint. Okay. And random is a package in Python that includes facts about, or includes functionality around randomization, and randint will generate a random integer on our behalf. So if we were to say response is an integer that is assigned randint 1 through, say, 4, or maybe let's do 0 through 3, and we were to print this response, if I were to run this program, I'm not even going to enter a question, but notice that it prints out 2. Try it again, it prints out 0, and so on. All right, so we're getting a random number between 0 and 3, inclusive of both of those numbers as our response. And so now we can actually implement this logic that we just saw on the previous slide, right? So if response is equal to 0, print most definitely. Right? Else, and we're going to nest this logic, if response is equal to 1, print highly likely. Else, if response is equal to 2, print ask again later. And finally, else, print no way, not a chance. Something really depressing. All right, so let me make this just slightly smaller so this all fits and pause right here. So the point of this code segment is to generate a random number, right, between 0 and 3. And then we are choosing one of 4 possible paths, right? So if that number is 0, we're going to print most definitely. If the random number is 1, we print most highly likely. 2, ask again later, and so on. And we see that there's only one of 4 possible outcomes here, right? No number that is generated can print multiple statements in this nested if then else statement for the reasons we just discussed. So if we were to try this, we could see if our program has a slightly more optimistic view of the future. I could try this again. Python 8 ball, ask a yes/no question. Will Alex get a 4.0 this semester? Let's try this one more time. I'm going to be a little bit more assertive here. Will Alex get a 4.0 this semester? It's got to be a bug in the program. Anyway, the point of all of this is to say, notice that if we had a real 8-ball actually has like 16 faces on it, and it has 16 different options for outputs, I believe. And you can imagine if we generated a random number between 0 and 16 rather than 0 and 3, this indented nested if then else statement would get very indented and very nested and would be very cumbersome to work with. And so the next piece of syntactical sugar we're going to look at today is called an elif statement. And again, just like with, and I want to show it to you first, and then we'll implement it in our code. So just like with the relative reassignment operator, this isn't giving us any new kind of capability, but it will clean up our code and make it look a little bit nicer. That's why it's called syntactical sugar. The idea is this pattern is very common, right? It's very frequent in your programs that you'll want to have a point where you need to make a decision to have your code go in one of many different directions. And rather than having to deeply nest them visually, we still want to be able to deeply nest the logic such that only one outcome is possible, but we'd really like to avoid all this indentation. So let's try rewriting what we had as a sequence of if, elif, finally else statements, rather than nested if, else statements. So I'm going to go back to my code. And all that you really need to do here is take the nested if statement and press backspace until you get to elif. And then we need to fix our indentation. And I think I may have talked about this in one of the videos, but if not, in code editors, if you select a number of lines of code and you press the tab button, you'll notice that it indents by 1. If you hold the shift button and press tab, it unindents by 1. Right? So we unindent everything because that's sort of the point. We're not visually nesting, even though we're still logically nesting. This is the same logic as we had before. And we can do the same thing to the next nested if-else statement. So here we see we have else if or elif response is equal to 2, print ask again later, else print no way, not a chance. All right? And so this is a much prettier little program. You'll notice that if you had 20 options, it would read very clearly. The key thing to remember is that L is short for else, and these do have to be related to a top level if. So if response is 0, we do something else. If response is 1, we do something else. And only one of these 4 possible outcomes here will ever occur based on this response. Any questions on elif? All right. So we've got one last exercise to move through today, which is the idea of a search, which is an algorithm. And to pull this off, I'm going to take out a very crispy $1 bill and describe to you that every bill on it has a serial number for when it was printed. And there are 3 digits at the end of this serial number meaning a number that must be between 0 and 999. And what I'd like to do is see if we can guess using some amount of logic and forethought what this number is, and whoever guesses it gets to win one juicy dollar. So who wants to take the first guess? Yep.
12.
Not 12, higher. Yep.
69. Sorry.
Not 69. Higher. Yep. The number is between 0 and 999. Higher. Yeah. Higher. Even higher than 420. Yep, up front.
650.
Lower. Yeah.
544.
Lower. Yeah.
112.
Lower.
473.
Lower.
412.
Higher.
458.
Lower. Yeah.
444.
Higher.
456.
Lower.
449.
Higher.
452.
Lower. All right. 2 more minutes on this, and then we'll talk through it together. Check with your neighbor. One more minute. All right. Let's talk through this one together. So this is a classic algorithm called a binary search. And I'm once again going to set up my stack with globals. And I've got a low variable that's initialized to 1 and a high variable that's initialized to 100. And in the previous example, if we imagine what would we initialize these values to if we were guessing between 0 and 999, that would be our bounds for the last 3 digits of a dollar bill. We would have some output here. For time purposes, I'm not going to print these first 2 lines. They're just sort of prompting the user. But if we were asking you to do this on the quiz, we would want you to write these out. We wouldn't ask you to write out English sentences like this. That's a waste of our time when we're working through quizzes. But this is meant to be a program that we're just sort of working through for fun. And you could try typing up. I would encourage you to after class. We then have this variable playing, which is a Boolean and initialized to true. And then we encounter a while loop. And this while loop on line 10, I'm actually going to get this out of the way, has a compound conditional, right? So you all learned about and, or, and not, which are our Boolean operators. And this and operator is saying, while playing, and so because playing is already a Boolean value, it either has to be true or false. So we can use it directly, right? We can say, while playing, we look up playing, it's true, so true, and we do need to go and evaluate the right-hand side of the and operator. Low is less than or equal to high. So low is 1, high is 100, low is less than or equal to high, that's true, so we're good to jump into this loop. I'm going to change color here so that I can write inside of the code and outside of it and still be visible on the projectors. Okay. So then we set up a guess, right? And what's the right strategy here? Well, we're kind of guessing halfway between what we know our bounds to be, right? And so right now we know our bounds are 1 and 100. So our guess is high plus low, so 101, integer division by 2. So 101 divided by 2 would be 50.5, right? But because we're using this integer division, we truncate the decimal. We just throw it out, right? There's no remainders in integer division like this unless we use the remainder operator. So we would just have 50 is our guess, right? This is our first guess. And we would print, and here I am going to keep track of this output. So the output here would be we print the string 50 question mark. Right? We turn guess into a string, we concatenate a question mark, and we would print 50 question mark. That's the computer's first guess as to what was this our number. And just for reminder purposes, we were imagining 18 as our secret. So we would respond to the request for input with lower, right? 18 is lower than 15. We would say, hey, computer, lower. And so result would initially be lower. Then we reach an if-elif statement where if the result is equal to yes, that's not true, so we go to the elif. Elif result is equal to higher, that's also not true. Else, we're going to go into the else block here and assign to high guess minus 1. So our guess was 50, but now we know that it's not 50, it must be lower than 50, so the next lowest number that it might possibly be is, let me actually, sorry, we're updating high here, so I'm changing 100 to be 49, right? So let me just break this down one more time. So our guess value was 50. We say, okay, 50 minus 1 is 49, and take that value and assign it to our high variable. So now we know that the answer must be somewhere between 1 and 49, right? So we've cut our search space in half in this fashion. So we go back up to the top, and we once again need to update our guess. So we take high plus low. 1 plus 49 is 50. Integer division by 2 is 25. So our next guess, right, is going to be 25. And we would print out that guess, so 25 question mark, and output. And here, when the computer asked us to respond higher or lower, well, we said 18, so we're going to say lower. So I'm going to just leave lower there. Lower would have been the result. So once again, we reach this if-else construct. We know result is not yes. We know result is not higher. So we reach our else block once again. And we say, okay, since it's actually 18 is lower than 25, that's the number we're trying to get the computer to guess at. So we take guess, which is 25, we subtract 1 from it, which would be 24, and assign that to our high. All right? We go back up to the top. And notice this is the same type of algorithm you all were thinking through and implementing in your head, but it's expressed with a while loop and if-else statements as a true algorithm in a program. So now we need to update our guess. So we take high plus low, so high is now 24, low is 1, so 25 divided by 2 would be 12.5. But we know that 12 is going to be the integer division of that, so 25 divided by 2 integer division is going to be 12. You just get rid of everything after the decimal. So we guess that number, 12. That's what the computer prints to us. And now we're going to respond higher, right? So when the computer says, is it 12? No, we're thinking of a number that's higher. So our result is going to be higher. And I'm just going to replace lower with higher here. I could have crossed it out and rewritten it below, but for space purposes, I'm just erasing, right? So we said higher, and now if result is equal to yes, that's not true. Else if result is equal to higher, that is true. So we go into this elif, and we take the current guess, which is 12, and we add 1 to it, so 13. And that's going to be the new low bounds, right? So now we know this guess must be somewhere between 13 and 24. All right. So we go back up to the top, and we once again need to test. And notice we're skipping over the else because we went into the else if here. We go back up to the top, and we do high plus low. So 24 plus 13 is 37. 37 integer divided by 2 is 18.5, right? We get rid of that 0.5, and now our guess is going to be 18. All right? So we print 18 question mark. And finally, we would respond as the user, yes. That is the number that we were thinking of in our heads. And this time around, we would print woo. And we're updating the playing variable to be false, right? So playing is no longer true. Playing is now false. And so when we get back up to the top, and something that I was kind of skipping past, actually, that I shouldn't have, is each time we go back up to the top of this loop, we need to reevaluate this Boolean condition. Is playing still true? Well, playing was true this whole time. We just now updated it to be false. So false and another value means we're done with this loop. But we should have also been checking, is low less than or equal to high? Throughout this whole time, low was less than or high. But you can imagine if you get to a point where that's no longer true, the user is being has given you the wrong wrong inputs, because that's sort of an illogical place to end up. All right, but because playing is now false, and any other value over here, it doesn't matter, is going to be false, and our loop would complete. I think we have time for one question on this. Yep. Good question. This question came up on chat as well. We don't write out the inputs even though those would show up. It's sort of either way. Technically, you certainly could write what's printed out as part of the input prompt. But what we type in as a user isn't technically output, so that's where it gets a little bit funky. And in our diagrams, we tend not to include the prompts of input. If you haven't started on exercise 02, I would encourage you to do so. Great work today, and we'll see you next week. Come by office hours if you need help.
Something. I'm wondering if this is normal, but on Gradescope, exercises are usually released like a day after it's actually is announced. Like before the first quiz, there was an announcement that said you should finish practice one because it's related to the content of the quiz. But I didn't actually get access to practice one until after the quiz. Is that normal?
So
Good morning. All right, welcome back, everybody. I've got 11 on the clock here, so we're going to go ahead and get started. Got a number of fun and exciting exercises to move through in class today. For those of you who are on stream, we've got questions going via Course.Care. Additionally, the slides for today, if you'd prefer to write on them when we're doing diagrams, they are posted under today's entry on the course homepage. We'll be looking at control flow practice today. And yeah, we've got currently a new exercise out. And just as sort of a refresher on sort of the cadence of our course, we tend to be async moving forward on Tuesdays. On Thursdays, we'll be here together practicing, writing example programs, things like this. Exercises will be going out on Tuesdays. They tend to correspond very closely with the videos and the lessons that you've learned, so they give you a chance to practice what was in those asynchronous lessons, and then are due the following Monday. Some of you have asked why isn't the autograder released immediately after the write-up? And the truth, the full answer is it just doesn't exist when the write-up does. So these are all new exercises this semester so far. And as soon as I get the exercise write-up done, I post it. And then as soon as I've been able to get the grader done for it, it's getting posted as well. We came into the semester, we thought we could use some of the old tried and true exercises we've done in the past, but Wordle captured my heart, and I thought, you know, this is the perfect way to start 110, so why not make new exercises, and that's sort of why the autograders come out a little bit more slowly. So today's goals are as follows. A couple of announcements to move through. We'll be practicing and reviewing if statements and while loops, and then we'll be looking at some new little sort of tweaks to what you've already known that will help you write more concise and prettier code called relative reassignment operators and elif statements. I want to remind you all that tutoring is available on Wednesdays and Mondays, and this is a place where you can come for as long as you'd like, work with us. On conceptual questions, go back over problems we do in lecture, go back over practice problems ahead of a quiz, review the quiz and the problems that you may have had confusion on. The schedule is always going to be on Course.Care, and it's just a walk-in, come as you wish, time where we'll have typically 3 or 4 UTAs staffing. The interactions will either be one-on-one or in small groups, and again, it's sort of relaxed. You can go over concepts. And it's a great place for the things that I mentioned earlier. The one limitation of tutoring is we ask that exercise help questions are brought to office hours. So tutoring's for conceptual help and understanding the fundamentals, whereas office hours tends to be where you can get one-on-one help with exercises. Along the lines of exercises, you can find the full schedule always on Course.Care. As you're working through exercises and run into roadblocks, come in. We tend to limit meetings to about 15 minutes, with the rationale being this is about how long it usually takes to be able to talk you through a concept that you might be stuck on. And it might not actually be like where you are that's like the roadblock that you're currently up against. It might be something a little bit more fundamental that will help you get there, but then give you a chance to go out and work on it on your own. As I've said many times over, the best way to do well in this course is to come to your own individual understanding of how to write programs and how to read programs. And so every bit of practice you can do individually will help you with that. If you come to office hours for conceptual questions, that's great, and we love to have those too. If there's not a queue of people waiting, we can be a little bit less restrictive on time, and we can work with you for a little bit longer. But if there is a queue of people waiting behind you, we will limit conceptual help questions to 15 minutes as well. In the past week, 170 COMP110ers this semester made use of office hours, so many of you have, I think about 1 in 3. The average wait time was 1 minute, and a standard deviation of 1.5 minutes. I already explained to you all mostly how this works, so just a reminder that you come to Sitterson Hall for this. Both Sitterson Hall and Fred Brooks are the exact same building. They're just 2 different sides of the same building. So if you see FB, that means Fred Brooks, SN is Sitterson. Everything happens on the first floor, which is the 0th floor in this hall. Any questions on tutoring or office hours? All right. There's one other announcement to get out of the way. There's an elephant in the room that needs to be addressed. I recently my heart was warmed by this yak of someone asking, and it was actually someone in the first section who came up and revealed themselves to me. If anyone else is literally obsessed with Wordle, I hope that you are, because it's a really fun game. I hope you're counting down to midnight. But I shared this on my Insta, and that made some people nervous. And to the person who said they would smile themselves if I was on Yik Yak, I just want to let you know you don't have to, because I'm an Android user. I don't actually have access to Yik Yak, sadly. But occasionally things get shared with me, which I do enjoy. And so what I want to say is that in a case like this, be sure, I'm all for speeding through videos if it works for you, but be sure that you're not getting less comprehension out of moving too quickly through content. But I'm not actually on Yik Yak because it hasn't come back to Android yet. All right, so let's jump right into a practice question. Here we've got a nested while loop where I want you to think through how this might work on your own, but notice that these things are nested. And again, these slides are on the website, so if you have a tablet and you prefer to write that way, that's totally fine. Otherwise, I would encourage doing this on pencil and paper. Let's spend a few minutes on this. We'll have UTAs around the room if you have questions and want to talk through things. Additionally, work with your partners, introduce yourselves, and we'll come back in another 5-10 minutes and talk through this together. Assume that the user input is 3 on line 3.
Exactly. Yep. You want to make sure you finish your loops completely before moving on.
As you make progress on this, feel free to, and as you already are, introduce yourself to your neighbors and talk through it with one another. Additionally, if you have questions on how something's working, we've got awesome UTAs here who can talk you through it. 2 more minutes on this.
Yep, exactly. Next one until it finishes. Right. Say, and that can be with that condition. Exactly. Yep. Does that make sense? Okay, awesome.
One more minute on this, and then we'll talk through it together. All right. I'm going to start working through this. If you didn't quite get all the way through it, that's okay. This is a longer loop to process. But just to be sure that we're able to get through today's content, I'm going to go ahead and get started. It's easy to want to jump ahead and start looking at code that happens, that's too dark, right in the middle of a code listing. But I'm going to encourage you to always start from the top and work your way down and just doing it as the computer would. So when we get to this, we'll talk about breaking it down. But first, let's start from line 1. We've got a doc string. We know that there's nothing really important there. That's just documentation for our purposes as humans. And then we see a declaration of I, where the user is giving us some input. And I should have gone ahead and set up my stack. And my stack is going to have a globals frame. Starting next week, we'll know a little bit more about other kinds of frames or adding more frames to our stack. For now, it just has this globals frame. And we'll learn about another area of memory as well called the heap. But for now, this is good enough. And we declare I. So I's initial value is, and we asked the user, we said it was going to be 3. So we asked for an input. That gave us a string. We converted that to an integer with the integer constructor and assigned the result of that to I. So now I's value is 3. We then initialized the variable named s to the empty string. And I want to point out that quotes in memory for strings are important. And this is something that in diagrams, on quizzes, we ask you to be very intentional about, so that if you have something of string data type, you put quotes around it. That way we know it's a string. If you have an int, you don't put quotes around it. That way we know it's an int. Don't put a decimal after it either. When we actually talk about output and what gets printed to the screen, we're a little bit more lax about whether or not you put quotes around things or not. We would generally encourage you not to worry about quotes in output, because when you run a program and you print a string, like your Hello World program, the printed output doesn't have quotes. It's all just text that goes onto the screen. Where we're really specific about this is in memory, in our frames on the stack, and on the heap when we get there. And so being very intentional and careful about quoting your strings and not your other data types will help you. All right, we then reach a while loop. And as you just learned, a while loop works initially kind of like an if statement, where we test whether or not this Boolean condition is true. So we see this reference to I. So we look up in memory, what is I? It's 3. Is 3 greater than 0? Yes, it is. That's true. So we go into this loop. And then we reach an important line, line 7. And I want to break this line down because there's a good question about this on the previous class. And there's some confusion around it. So on this line, a student asked, so let me do this correctly first and then talk about a common misconception here. So what we're doing is we need to complete the right-hand side of this assignment statement first. We look up S. S is currently the empty string, so it's as if we're concatenating empty string with H, right? And the result of that is going to be just the string H, right? And so S would be replaced with H. That's sort of the correct progression that you would expect here. And the question was, why would this not result in the string sh? Okay? And this is where quotation and things become very important to understand when you're looking at reading a line of code. So you'll notice that there's no quotes around this s, here. And what that means is we're referring to an identifier or something that should have its name bound to a value in memory. Otherwise, we've got an error in our program. So when we see this s that's unquoted, we go and we look up, oh, what's the current value of s in memory? Well, it was previously the empty string, so that's why we substitute the empty string there. We use the value h as a string value because it was quoted. So we're not using a variable named h, even though later on in our program we'll have a variable named h. We're using the string h here, and there is a difference between a variable name and a string value. Right? And if that feels like something that feels a little bit uncomfortable to you, I would encourage you to come talk with us and work that out in office hours, because that's very important to understand the difference between those two. On the next line, we set up a variable named h and initialize it to 0. There are some questions in the previous section around this as well. Namely, if h is defined inside of a while loop, do we need to do something special about it versus have it in globals? And for our purposes in Python, we're just going to keep it in the current frame. In other programming languages, you would potentially do other things with this and have different rules around what we call scope. We will learn some scoping rules in Python soon enough, but for our purposes, declaring an h here is no different than outside of it, and so we'll continue on. We then reach this nested while loop. And notice it's important to before you process a while loop, know where it starts and ends. So this outer loop started, its body started on line 7 and ended on lines 12. Whereas this inner loop, its body is starting on line 10 and ending on line 11. So there's 2 lines inside of it. And importantly, this last line is not a part of it. All right, so let's jump in and see whether or not this test is true. So we need to test, is h less than I? We look up h, it's 0, I is 3. 0 is less than 3, that's true, so we go in. And we reach a very similar concatenation statement where we're saying, take the current value of s, which is the string h, concatenate e to it, and assign that back to the string s. So s is now going to be the string he, and it's been updated. H is going to be h plus 1, so h is no longer 0, it's now 1. And we reach the bottom of this loop, and this is the most important part of this little code exercise, which is when you reach the end of a loop, you go back and you test its corresponding statement or Boolean condition. And here, we haven't finished processing this innermost loop, so we need to go back and test, is h still less than I? We're not going to jump all the way back up to I greater than 0, because that wouldn't really make logical sense. So we're going to focus on finishing this inner loop first and being sure that h is still less than I. And if so, then we need to keep looping. So we test is h less than I, h is 1, I is 3, so that's true. We go into the loop. And then here I'm going to start to move a little bit faster. We know that this line adds another e to our string s. Right? So our string s is now the string hee. And h is going to be updated to be 1 more than it was, so h is now going to be 2. And then we go back up and we test again. Is h less than I? Well, h is 2, I is 3. That's still true. We go into the loop. We add another e to our string. And we add 1 to h. Right? You'll see me crossing these things out. If you'd prefer to just erase, that's fine. And typically on like a quiz problem, you wouldn't have quite the length of strings that we're building up here to be concerned with. But let's go back up one more time. So now h is 3, and we test is h less than I. Well, h is 3, I is 3. 3 less than 3 is now false, so we're done with this loop. And we're going to continue on to line 12. Right? So we're going to exit that innermost loop and continue to line 12. And I'm just going to circle this line and say we're coming right back to it. But let me pause right here and ask if there are any questions about what we've done so far. All right. So on line 12, we are taking i's current value, which is 3, subtracting 1 from it, and reassigning it back to itself. So I is no longer 3, it's now 2. And at this point, we jump back up to the top of the outermost loop, and now we need to ask the question of, is I greater than 0? And 2 is greater than 0. So we're still looping. We go in, and here we reach that concatenation statement. So we're saying, what's s's current value? S's current value is h followed by 3 e's. So we're going to take that same string and concatenate an h onto the end of it. So now it's going to be h, e, 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 h. And h is going to be reset back to 0. So I'm just going to reset the value of h back to 0. And we once again reach this innermost loop. So h is 0 less than 2. That's true. We go into this loop, and once again, we're adding an e on, or we're appending to the string s, so that it's now h, e, 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 h, e. Oops. And we are incrementing h by 1. You'll notice that this inner loop is counting up, and we're counting up until we reach h no longer being less than I. And that's a pretty common way of looping. And then the outer loop is counting down, and we can talk about that in just a second. We have to test again, is h less than I? So h is 1, I is 2. That's true, right? So we go into the loop one more time. We add another e to the end of this string that we're building up. So he. And this is an example of concatenating to grow a string. You need to do this in the current exercise, the Wordle exercise, where you're adding emoji onto the end of your string. Very similar strategy for doing that here. We add 1 to h, so h's value is now 2. We go back up and we test again. Is 2 less than 2? And finally, we finish this inner loop once again. So we're not going to loop here. We continue on to line 12. We take i's current value, which is now 2. We subtract 1 from it, so it's 1, and we replace that in memory. So notice I is counting down, and hopefully we're making progress towards this loop. The outermost loop, when we go back up and we test again, is I greater than 0. Well, notice we're counting down. We're getting closer and closer to 0, so we are making progress. This isn't an infinite loop. We're about to be done with this, but we still have a little bit more work to do. So we go into the loop one more time. We add an h to the end of this string, so now it's h, e, 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 h, e, e, h. And we once again reinitialize h to 0, so h is now 0. And we test, is 0 less than 1? That's true. So we go into the loop. That's the innermost loop. We add an e onto the end. So this is starting to get pretty long. But you'll notice there's a pattern here. H followed by 3 e's, h followed by 2 e's, h followed by 1 e. We increment h by 1, so h is now going to be 1. We go back up to the top. We test is h less than 1, or sorry, it's h less than I. 1 less than 1 is false, so we're done with the innermost loop. We subtract 1 from I, so I is now 0. We go back up and we test again, is I greater than 0? That's now false. So we would print s, and the printed output would be h, e, 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 h, e, e, h, e, and that's our output for this program. If I can spell. One of the other questions that came up in the previous lecture was, do you need to add output to the screen for when we ask the user for input? And typically in exercise on quizzes, we wouldn't expect it, but if you want to, you can. What's a little bit weird about input lines is, yes, there's going to be some output on the screen that's prompting you, but what you type into the screen isn't actually technically input, even though it also shows up, or isn't technically output, even though it also shows up on your screen. That's input. And so to avoid that confusion, we just say the only lines that you need to trace as output are print lines. Any questions on this example? So here we're seeing a nested loop. And the thing that is conceptually tricky about nested loops when you start to think through them for the very first time is remembering that you need to fully complete an inner loop before you continue on past it. And so paying attention to the indentation is important, and being careful of that. You will have a nested loop in the current Wordle exercise that's out, exercise 02. Additionally, here's an example of counting up in an inner loop and down in an outer loop. Ultimately, you can write loops that do all sorts of carry out various patterns for iteration. What's important is that they ultimately complete and aren't infinite loops. So this brings us to a new concept that I want to introduce to you today, which is reassigning a variable relative to its current value. So this is something that you commonly do. We saw it on a number of lines in this last example, but here are some examples. So if we wanted to write a loop where we counted up by 2 each iteration, we could say I is assigned I plus 2, or I is assigned I minus 1. We saw that in the previous example. You can imagine having some variable that's keeping track of a summation, and maybe your total dollars is assigned total dollars plus next donation. Or we're doing some concatenation where we're building up a message to send in some string variable, and we have to take the current value of the string, concatenate some exclamation points, and reassign that back to itself. This pattern is very common, where we're saying relative to the current value in a variable, add it, change it, do something to it, and then reassign it back to itself. And so this becomes kind of tedious to type out. Like, sure, these first 2 examples, I is assigned I plus 2. There's not a lot of tedium in writing I a duplicate time. But as your variable names are hopefully expressive of the problem that you're trying to solve, and as we learn some new constructs, it can become pretty tedious and leads to typos, potentially errors, to have to write it out twice. So Python, as well as many other programming languages, have what's called a relative reassignment operators, where these 2 lines are performing the exact same operation. So I is assigned I plus 1 can alternatively be written as I plus equal 1. They mean and do the exact same thing. You don't gain any new capabilities, but your code is a little bit shorter and sweeter, which is why this is called syntactical sugar. There are many, and where this starts to become more useful is if you have longer variable names, such as total dollars. You can see total dollars plus equals next donation is incrementing or increasing the value in total dollars by next donation. This works for all the arithmetic operators that you would expect, works for concatenation, and some others that you would less commonly use, but is a common idea not only to Python, but many other programming languages as well. Any questions on relative reassignment operators? We'll see them in some of the other examples today. Just a little shorthand. So the example we just traced could have been rewritten using these. This is in the slide deck for reference if you want to come back to it. All right. So the next exercise I'd like you to think through and discuss with your neighbors is we've got 2 different code listings. And the question is, can you imagine a value that you can assign to this response variable, one value where you could evaluate both of these, left-hand example and right-hand example, and come up with different printed outputs given the exact same response as an input. So think about this for a moment and discuss with your neighbor whether or not you can imagine a response value that would lead to different outputs in these examples, and then discuss why that might be and what is the true fundamental difference between these 2 examples. So we'll spend a few minutes on this, and then we'll come back and talk about it together. If you want to confirm your thinking with a TA, raise your hand. We'll come talk to you about it. One more minute on this, and then we'll discuss together. Twenty more seconds, and we'll talk about this together. Have an answer ready whether or not these would produce different output. All right. So by a show of hands, could you identify an output that would produce, or an input that would produce different output? Raise your hand if you could. All right. Seeing a lot of hands, and that's good because you can. You can get a different output given the same input here. And this is a very common source of confusion in the early days of programming, when you have sequences of if statements versus nested if else statements, and sort of the relationship between these two things. So on the left-hand side, does anyone want to posit what's an input that would give you a different output? 0 or 1. All right. So yeah, absolutely. So let's try 0. So if we imagine response is 0, if response is equal to 0, then we would print most definitely. Yep, that would happen. Because this next if statement is not connected in any way through an else, we go on to that if statement and we ask, okay, is response equal to 1? No, response is 0. It's not equal to 1. So we skip over the then block. We then reach a completely unrelated next if then else statement, and we ask, is response equal to 2? No, it's not, but this does have an else, so we're going to print nope, right? So both of these lines would evaluate and print as output given an input of 0. And that behavior is quite different than what we see on the right-hand side. If response is 0, we go into this. This is true, right? Response is equal to 0, so we would print most definitely. But then notice we reach this else. And everything in this else block, all of this nested logic, would only evaluate if response was not equal to 0. So none of that gets evaluated when response is equal to 0. On the right-hand side, only one of these 4 possible outcomes is going to happen. Whereas on the left-hand side, each of these 3 if statements are unrelated, and so that last else would have gotten evaluated, just like we saw. This is a source of potential errors, like we probably didn't mean to print nope in the left-hand side example here. And so we tend to be careful when we reach a point in our program where we want to express only one of many different paths can happen. You tend to want to or need to use a nested if-then-else statement. So if one thing's true, we'll do something else. If something else is true, we'll do that else. If something else is true, we'll do that. And only one of those 4 paths will ultimately be evaluated. Questions on this example? All right. Another reason for this, you could imagine, this, instead of being else, if this was if response is equal to, say, 4 instead, and this would still be suboptimal, right? Even if, and the reason for that is, we know that response should be only one of these 4 possible options, but in the first example here, if response was 0, well, the computer is still going to check after it knows that it's 0, is response equal to 1, is response equal to 2? So there's some additional processing that would happen that wouldn't need to happen if you had properly nested it, such that on the right-hand side, as soon as it figured out which branch it was taking, it could skip over everything else. All right. So the next thing we're going to do together, and what I just said and is available in notes and on the slides, is effectively, you really when you reach a point where your code needs to go in one of many different directions, but should only go in one of those directions, you want to connect those possible directions via nested if-then-else statements. And we'll learn a new way of doing this a little bit more cleanly in just a moment. But this is the main logical goal here. This is the only way that you'll get most efficiently get going in one of many possible different directions. All right, so next we're going to try implementing a little program to simulate an 8-ball. So an 8-ball, as many of you have seen, a magic 8-ball is one where you can ask it a yes/no question, shake it, and magically, through an oracle of knowledge, a response to your question will be answered and raised through a window in the 8-ball on the back side of it. So who in the audience has a question to ask the 8-ball today? Has to be a yes/no question. Yeah, up here. This is a dangerous question to ask an 8-ball. And what's your name? Pass COMP110. I'll tell you that there was an Alex in the previous section that asked if he would get a 4.0, and it was definitively no. But good news for you, signs point to yes, great. That's much more optimistic than, I mean, literally we tried 4 or 5 times, and it was always negative. So you get the point. AJ will pass COMP110, and so yeah, let's try implementing this in code. So if you want to open up VS Code to follow along with me, let me actually close this out and delete my previous example. Forgot to do that. In the lessons directory, we're going to create a file named 8ball.py. All right. And just as a sort of quick reminder, whenever I'm working in a file, if you want to know which directory I'm in or which directory you're in when you're working with any other file, all of that information is contained on the line below a tab. So this is telling you it's in the lessons directory and the file name is 8ball.py. Right? So we'll go ahead and we'll start our program off with a doc string, which is magic 8-ball oracle of truth about the future. Yeah, something that describes the program we're writing. And the only really important concept that an 8-ball actually has as a part of a physical object is there's some entropy or randomization to it, where you shake it, and that's what's causing an unknown physical process, a little bit of entropy to cause one of the faces of the die that's inside of it to raise to the top. So we need a way of providing some randomization. And what we're going to do is we're going to import some functionality from the random library of Python in order to do so. We'll talk more about importing in the future so that you understand fully what's going on here. But for now, we're going to import a function named randomInt, or randint, which can generate a random integer on our behalf from the random library. So that's what that line means. Again, we'll talk more about this in the future. This is good enough for now. So we want a program that allows the user to ask a yes or no question. So we can ask for input. So input, ask a yes or no question. All right. You might be thinking, Chris, why aren't we storing this input in a string? Well, it's part of the wisdom of an 8-ball. It's not actually listening to you. It's just giving you a random response, but it still feels like there's some knowledge in there. So we're not going to store this result in a string. You could imagine, if you wanted to play some fun tricks on your friends and roommates, pre-programming various responses based on the questions that are asked and trolling them a little bit. But for now, we're just going to keep this simple. And all we really want to know is what is our random response going to be. So we'll set up a variable named response. That will be an integer. That will be the result of calling the randint function with, say, 0 and 4 as our bounds. So this randint function, when our program runs, is going to generate a number between 0 and 4. Actually, that should have been 0 and 3. We only really want 4 options here. So it'll be inclusive of 0. So it might be 0, 1, 2, or 3. Right? So 4 possible options here, inclusive of both of these ends of the range. And so now let's write that if statement that we saw earlier. So if response is equal to 0, print, yes, definitely. Else, if response is equal to 1, so we're going to do this nested like we just talked about, print looking hopeful. Else, if response is, else, if response is equal to 2, print doubtful, or ask again later. That's a little bit better. And then finally, else, print no way, not a chance. All right. And I'll pause here and save my program. But notice we've got this nested if-else structure where we really want only one of 4 possible responses, and it's going to be based on this random number that is being generated behind us. We don't really know how that works, but that's OK. It's part of the, we could go look up the documentation for it. That's the beauty of abstraction. We can use somebody else's abstraction to implement this functionality. We just know this is going to give us a random integer between 0 and 3 inclusive. And then our nested if-then-else statement ensures that we only print one of these possible options, depending on what that value is. And as soon as we know that it was, say, 0, we're not going to waste the computer's time checking anything else. We're going to skip past those nested else blocks. All right, so let's try running this program and seeing if it works. Poor Alex. Really got the poor end of, I mean, even when we asked this program about the 4.0, didn't work out for him. Let me see if I can scroll this in such a way that it keeps everything on the screen. All right. So I run my program. Ask yes, no questions. Somebody else have a question for the 8-ball today? Yep, up front. Will I guess the wordle of the day? And the response was looking hopeful. Good, optimistic answer there. But you could try this again and notice if I were to ask, will I get it on the first guess? And we expect, no way, not a chance. So maybe there is some wisdom in this. There's no wisdom in this. It's just randomization, right? Before we move on to cleaning this up with a new construct we're learning today, any questions on what we see here so far? All right, all right. So you can imagine an actual 8-ball has like 16 different possible outputs, I believe. And if we generated a random number between 0 and 15, we could keep extending possible different outputs to have all of the different messages that a real 8-ball would have built into it. But if we use the same strategy, notice that it would start to feel like we were getting pretty deeply indented, and it would be hard to read our code, and it gets a little bit out of control. Because of this, we actually have a nicer piece of syntax at our disposal, and I want to show you that before we go and implement it together. So there's a construct called an elif statement that stands for else if, and what you see on the left-hand side is exactly equivalent to the right-hand side logically in terms of how this program snippet will behave, but it's much more pleasant to read and work with in code than deeply nested else if statements, right? So the idea is rather than having to say else and then enter a new level of indentation and then write another if else statement and keep doing that forever and ever until you reach all of the cases that you want to handle, we can start with an if statement and then follow it with elif statements where we can test these conditions and ultimately end it with an else if we want. And it can clean up our code pretty nicely, especially if you imagine, like I said, 16 options where this would have been very deeply nested. It'd be much nicer to work with elifs. And we'll be seeing elifs through the rest of the semester, so let's go ahead and try working out our program such that it uses that in step. So the key idea here is if you take an if statement and you just effectively bring it back up to the else, delete it so that it says elif. But notice then your indentation is a little bit off. And so what I would encourage you to do is select all of the text that's indented. And I think I've talked about this in a video, but just for repetition's sake, if you press the tab button, it will indent all of your text. If you press shift, if you hold down shift while pressing tab, it will unindent by 1. This is true of just about every code editor. And that way we can unindent a whole block. And we can do this just the same with the following if statement. So I'm going to bring that one back up to the top. So elif, response is equal to 2. And then select the 3 lines and unindent those. So notice that this actually starts to read much more nicely and looks a little bit less cumbersome. If response is 1, do one thing. If response is 0, do one thing. If response is 1, do something else. If response is 2, do something else. Else, do something else. And you could keep adding other cases, and the logic would work the same as before, but the code is cleaned up. Any questions on this? All right. So this is elif. That's the second sort of syntactical sugar we've learned today. The other was relative reassignment, and we'll see both of these ideas in the next example. All right. So the next thing we're going to look at is the idea of a search. And to do this, I need to get out a crispy $1 bill here that one of you lucky contestants today is going to take home. Wealth building starts today. So every bill in the United States has a serial number attached to it. That's a very long number. We're going to be focused on the last 3 digits. So the possible values that this number could be are going to be between 0 and 999, 3 digits that we're working with. And I'll tell you whether or not a guess should be lower or higher. And we're going to go and take guesses from the audience. And the person, and I'm going to encourage you to do this in a rational, thoughtful manner. And the first person to guess it wins a crispy $1 bill. So who wants to take the first guess? In the back. 500. Lower. 370. Lower. 273. Lower. 124. Higher. Yep. 200. Higher. 241. Lower. 233. Lower. 225. Higher. 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 Yeah. Great work. Hand this to the fine young gentleman back there. Don't spend it all in one place. So you'll notice that a strategy quickly took hold that you all are familiar with in playing a guessing number game like this, where the first guess was 500. And 500 immediately eliminated half of the whole search space, eliminated 500 possible other guesses, such that now we've reduced our search space by half. And that process continued on, mostly in a very logical way. But this is an algorithm that we can program, and actually we're going to walk through this program and trace through it. And it's just called a binary search, because we have one of 2 possible outcomes. It's either too high or too low, or I guess there is a third outcome, which is you got it right on the head. In this code listing, you're going to see that we are reducing the search space between 1 and 100. We're going to go ahead and this is a program that's attempting to guess the number you're thinking of. So if you wrote this program, you could think of a number, and the computer would try and guess at it. For the purposes of tracing through this together in an environment diagram, we're going to assume that the number that is our secret number that we're thinking of is 18. And then I'm also going to ask you on line 13, when the computer asks, was my guess too high or too low, or was it correct, that you'll respond correctly there. So when the first guess is 50 and our secret number is 18, you would assume that the string on line 13 is going to be lower, right? So I'm going to encourage you to try working through this on pencil and paper. We got plenty of time to get through this, and then we'll talk through it together. I'll say that the line 6, you don't have to worry about writing that out as output. Just focus on the variables and then what gets printed inside the loop. 2 more minutes on this, and then we'll talk through it. If you think you've gotten through it, compare yours with your neighbor. One more minute on this, and then we'll talk through it together.
It's still going to stay less than the high. Right. Yeah, exactly. Even though you're missing Elif,
Still only going to be one of those that'll happen, not both the Ellis and the Ellis. You're right, then it would be 51 to 49, and then that would make sense. So you have just line 18.
All right, let's talk through this real quickly, because there's some clever things going on here. This is a very classical computer science algorithm for searching for something called binary search. And we'll see other uses of this in the future. And it sort of embodies the type of computer science algorithmic thinking of reducing a search space by half and trying to make progress as quickly as possible. So we start out with 2 variables, low and high. Low is 1, and high is 100. And the way that you think about these variables is that they're sort of the bounds that we're searching within, right? And ultimately, our strategy is going to be, as we learn a little bit more about where the thing that we're looking for isn't, we'll restrict our bounds to where it still could be by narrowing in closer and closer. Okay? As I said, I'm not going to print this output. I'm not going to write it out on the screen. On a quiz, we wouldn't ask you to write out a long string like this. That'd be silly. And then we're asking the user to press enter to continue. So we've thought of this number. We're thinking of the secret number 18. That's nowhere in our program. That's only in our head as us, the end user of this program, thinking about it. We then set up a playing variable that's a Boolean, and it's initially true. So you can think of this as sort of representing whether or not we're still searching, we're still looping. And once we find our answer, we'll set that to false, and that'll have some implications on the loop. When we get to the loop, and I'm going to need to change colors here. I shouldn't have started in red. Sorry about that. When we get to the loop, we see that we have a compound Boolean statement. So you learned about and, or, and not. Those are our Boolean operators. And here we're saying, while playing, and notice we can do this because playing is either going to be true or false, just by virtue of being a Boolean value. So we're asking, is playing true? And yes, playing is true. So we then need to look at the right-hand side of the and, because for an and, we need both sides to be true. Low is less than or equal to high. Well, low is 1, high is 100, so that's true. So we go into the loop. Now we need to set up our guess. So the guess is high plus low, so 101, integer division by 2, right? So regular division, this would be 50.5, right? But because this is integer division, we ignore anything after the decimal. We truncate the decimal, and our guess is going to be, our first guess is going to be 50, all right? So guess is 50. All right. And then we print, and here I am going to keep track of my output. So in output, we're printing 50 question mark, right? That's the first guess the computer's making. And It's our job to respond with yes, higher, or lower. So let me actually extend my frame here. So I need to provide this input. So the result would be, again, assuming that we are thinking of the number 18 and the guess was 50, 18 is lower, so we're going to respond lower. All right, so that's the string that we would respond on line 13, stored in the result variable. We then reach this if-else statement, right? So we ask, is result equal to yes? We look in memory and we see, no, result is lower. That's what the user just told us. So we go and we evaluate the elif statement. Elif, result is equal to higher. Well, it's not equal to higher, it's lower. So then we go to the else statement. And the else statement is doing something pretty clever that we need to be careful about. It's saying, take our current guess. So our current guess is 50, right? Subtract 1 from it. So that's going to be 49. And assign 49 to our high variable. So notice high is no longer 100, it's now 49. And notice what we've done. We've learned that 50 was too high, so we can eliminate everything between 50 and 100 as a possibility in the space that we're searching in now. So now the bounds that we're searching in is between 1 and 49, right? So we reach the end of this while loop and we go back up to the top, and we have to evaluate this statement, this Boolean again. Is playing still true? Yes. And is low less than or equal to high? Well, 1 is less than 49, so that's true as well. We're continuing to guess at new numbers. So now our guess is going to be 49 plus 1 divided by 2. Our guess is going to be 25. Okay, so we update guess to be 25. And we print that guess. So the next guess is 25. And the computer asks us to give it a hint. Did it get it, or higher or lower? Well, 25 is still too high, so the next guess should be lower, right? So we say lower. The number we're thinking of is lower than 25. So I'm going to leave the result string as lower and continue on. Once again, we reach this if-else statement. If the result is yes, well, it wasn't, so we look at the elif. If the result is equal to higher, it's not that either, it's lower. So we go back to this else, and we do the same thing again, right? We take our current guess, which is 25, subtract 1 from it, 24, and reassign that back to high. So high's value is no longer 49, it's now 24, right? That's the result of line 20. So again, we just said it's not in half of the numbers we were thinking it might be. We've reduced our search space by half. It now must be a number between 1 and 24. Let's go back up to the top and keep continuing this algorithm. Playing is still true, and low is still less than high. 1 is still less than 24, so we're still looping. We go back in, we need to come up with our next guess. So now it's high plus low. So high is 24, low is 1, 25. 25 integer division 2 is 12.5, but we throw out the 0.5, so it's just going to be 12, right? So our next guess is going to be 12. And we print 12 question mark as the next guess. This time around, though, when the computer asks us, is it 12 or is it higher or lower than 12, we would respond with higher because we were thinking of 18. Right? So I'm going to update my result string to be higher. And then we test if result is equal to yes. Well, it's higher, so that's not true. Else, if result is equal to higher, that is true this time. So we are going to evaluate this condition on line 18. We go into this then block. And we're saying, OK, take the current guess, which is 12, add 1 to it, so 13, and reassign low to be that. So now we're saying it's the low bounds on this is no longer 1, it's now 13. All right, so we know the number is somewhere between 13 and 24. Notice we're going to skip over this else because we evaluated the elif, so we don't go into that else block, and we go back up to the top. Once again, playing is still true, and low 13 is less than high 24, so that's still true. We go in and we need to make our next guess. So our next guess is 24 plus 13, so 37, integer division 2, which is 18.5, but again, integer division means we only focus on the integer and we throw out the decimal. So our new guess is going to be 18. And the computer is going to print that out. So it asks us, I'm just going to wrap around, 18. This time around, it is correct, right? So we would respond with yes. So result is no longer higher. It's now yes. And we go into this if statement. If result is equal to yes, well, now that is true. This condition does check out. So we would print the string woo, exclamation point. And we set the variable playing to false. So playing is no longer true. It's now false. Because this elif and this else are all connected, we don't even go look at those things, right? We don't test if results is equal to higher. We don't go into that else. We skip right past it. And we go right back to the top of our loop, right? And now we test while playing. Well, this time around, playing is false, right? We just set it to false. False and any other value is going to be false. So even though this is true, false and true is ultimately false because of the and operator. So we're done with this loop, and we continue on. And so in 4 guesses here, the computer was able to correctly identify the number we were thinking of. And this is the most efficient way of guessing towards, on average, any number in some range. This algorithm continues to work. Even if you plugged in 100,000 or 1 million, computer's happy to guess at your number and making optimal choices along the way. This is an example of an algorithm, which is one that you've thought through before in playing these types of number games in other classrooms. Questions on the example we're seeing here? So you'll notice this made use of the if, then, else, and elif statements here, which you'll be seeing a lot of in the future. And this is a clever and nice use of the integer division. I think it's a good program to type up and play around with and try out at home as well. All right, well, that's all we've got for today. Get started on exercise 2 if you haven't already, and great work in today's lecture.